So I'm going to go over a couple of different NLP topics today. So really there's a couple of different or like really 5 or 6 steps whenever we're doing any NLP process. First is the text collection, whether it's through a CSV file, whether it's through an API that you're pulling data from, whether it's through web scraping, whether you're gathering text data from a specific source, whether this data is social media data, Twitter tweets, or whether it's reviews on the internet that you're web scraping. The first critical step of NLP is obviously the text collection. And how you do the text collection is going to influence a lot of step two, which is about text pre-processing. So if you're filtering Twitter tweets or you're getting Twitter tweets, there's going to be emojis, URLs, ads, hashtags that you're going to want to clean up before moving further into the NLP pipeline. This stage also encompasses lowercasing the different words, making sure that every single word or every single letter in the word is uniform, and also removing punctuation, removing stop words. So stop words are things like the, is, in, at. These are words that don't really add much meaning to the semantic meaning of the sentence. And so removing those words will help alleviate a lot of the data load. Removing URLs and emojis, as we mentioned. Third step is tokenization. So this is all about splitting the text into different words. So I love NLP will be split into the different words I love and NLP. There's different tokenizers and ways you can tokenize, but crux of tokenization is you want to split a given sentence or a collection of words into the different words, into a vector of words. Fourth is stemming or lemmatizing or lemmatization. This reduces words to their base form. So there might be many different words that have the same base, and we want to make sure that all of those words, the meaning is the same. And so, for example, if you have runner, run, running, uh, run a marathon, or something like that, we want to make sure that those words, the base root that is run, is captured in all of those words. Just so we don't have running as a separate word from run, as a separate word for as a separate word from runner, right? The main of that, the crux of that is run, the root of that is run. So we want to preserve that semantic meaning in each of those variations of that base word, which is run. And so that stemming typically refers to just cutting off the prefixes and suffixes, whereas lemmatizing actually returns valid words. So it might be the case that when you're stemming, you may get to a base form that's not actually a word, but it's a common like prefix in all of the words. But when we're lemmatizing, we're making sure that what we return is actual valid word. So in the case of running, we're making sure that run is returned because that's the root, the base of the words. Next, we have part of speech tagging, which is identifying what part of speech each of the words relate are. So when we tokenized our I love NLP sentence into I love an NLP, we associate each word with its part of speech, so pronoun, verb, or noun. Next, we have named entity recognition. So this is all about categorizing a sentence or a group of words into entities or into specific topics, names of people, locations, organizations, particular dates. So in the sentence that we have Barack Obama was born in Hawaii, the entity, the person entity would be recognized as Barack Obama. Location entity would be identified as Hawaii. So within a sentence, within groups of sentences, how can we identify or classify these different entities from these sentences? So that's named entity recognition. Next, we have word embeddings. So obviously, when we're doing NLP models, when we're doing any machine learning model on text data, we can't just do it on the text itself. We need a way to convert that text into a vector representation, and that's where these different word embeddings and different algorithms to do that are. One famous technique is word to vec out there. And really, the purpose of word embeddings is we want similar vectors to capture similar words. So, for example, if two words are very similar in their meaning, those two vectors would also be similar. And these are high dimensional vectors, and we want to make sure that like similar words that have the same semantic meaning also have similar vector representations that we're so such that we're able to capture the meanings of those words when we're running our model. Now, when we talk about proofs, there's many different ways you can prove statements. We've gone through proof by induction. There's also proof by contrapositive. There's also proof by contradiction, which we'll be going over here today. So contradiction is all about taking a statement and looking at its contradiction and showing that that contradiction can never hold true, can never be true. And when we prove that, hey, that contradiction can never hold true, it will always be false, that's a way to prove that the original statement is true. So as an example, if our theorem is there is no rational number whose square is 2, or the square root of 2 is an irrational number. If that is our theorem that we want to prove, we first assume that, hey, there is a rational number whose square is 2, or the square root of 2 is rational, right? We want to assume first that the contradiction is true, and then we go through our steps to prove that the contradiction can never be true and it's always false. So we assume that, hey, there is a rational number whose square is 2. Then we simplify that further to, okay, saying that, okay, there's two integers, p and q, that we can represent this rational number as. P over q squared equals 2, where p and q have no common factors, because if they did have common factors, we can simplify them even further to their lowest terms. So p and q, p over q squared, are the two integers that make up the rational number whose square is 2. Then we multiply q squared to both sides. We get p squared equals 2q squared. We know that p squared is even because it's divisible by 2. So p must also be even, because we know that the square of an odd number is odd, the square of an even number is even. Since p squared is even, and we know this because 2 is a common factor. Because p squared is even, p is also even. So because p is even, p can be represented as 2 times integer r. If we replace p equals 2r into the original original equation of p squared equals 2q squared, and not the original equation, but the equation one layer from it, we get that 4r squared equals 2q squared, and then from that we get 2r squared equals q squared. Now we have shown that q squared is even because it's 2 is a common factor, right? We're multiplying 2 times by r squared to get 2q squared, or to get q squared. And so because of that, we know that q squared is divisible by 2, which means that q squared is even. If q squared is even, as per similar logic from above, we know that q is also even. And so now what we have shown is that we've shown that q is even, and we've shown from previously that p is also even. So because we've shown that p and q are both even, we've shown that p and q both have a common factor of 2, because they're both divisible by 2. But in our earlier assumption, we've said that p and q have no common factors. So because we violated that assumption, we know that this cannot hold true, right? We've shown that p and q have common factors, but that was our assumption from the beginning. So we've shown that this entire contradiction cannot hold true. We've shown that the assumption that, hey, there is a rational number whose square is 2 cannot hold true because of this contradiction that we've shown that p and q are both even, where in the beginning we've assumed that p and q have no common factors. And we've shown that they do have a common factor of 2 because they're even. So this is proof by contradiction. Now let's get into a Leetcode problem. So happy number. So the entire purpose of this problem is we have a number, let's say 19, and the number is considered to be happy if we consider each of the digits, take the sum of the square of those digits, and keep on taking the sum of the squared digits. And if at any point we get to 1, that means that that number is considered a happy number. If we end in a loop, or if we get to a point, or if we do not get to 1, then we do not consider that number to be, quote, happy. And so how can we do this? So for example, for 19, we take the digits, sum of the squares of the digits, 1 squared, 9 squared, we get 82. Then we take sum of the square of those digits, 8 squared, 2 squared, we get 68. Sum of the square of those digits, 6 squared, 8 squared, we get 100. And then sum of the square of those digits, which will be 1. And because we have ended at 1, we can return that 9 is a happy number. We can return true. So how are we able to do this? First, we create a helper function to get the sum of the squared of digits. So this helper function will allow us to get from 19 to 82, from 82 to 68, from 68 to 100. It's going to get us the sum of the square digits. And the way that we're getting that is by getting the last digit, by trimming the last digit, and then adding the square of that last digit, trimming the last digit, and then getting the last digit again, trimming that last digit again, getting the square of that, adding it to the sum. Right? So initially we have our sum to be 0. As long as our number is greater than 1, we're going to get the last digit, square it, and add it to our sum, trim that last digit, and then repeatedly do this until we run out of digits, or until num is greater than or equal to 1, right? Or until num is less than 1, right? So if we have 19, as an example, if we have 92, or 92 as an example, we're going to take the last digit, so mod 10, we're going to take 2, we're going to square that, add it to our sum, so that's going to be 4, and then we're going to take the 9, or we're going to trim that 2. So the way that we're going to trim the 2 is the 2 is by subtracting the last digit from the number. So minus 2, that's going to get us 90. Now to completely trim it, just get it to the 9. We're going to divide by 10, and that's going to give us 90 or that 9. And then we do the same procedure. And so that's our helper function to get the sum of the square digits. Now in our while loop, we're going to do this around 10 times. And the 10 is a number that I experimented with that works for this problem. So in those 10 times, we're going to call this helper function. We're going to keep on taking the sum of the square digits. And if at any point we get to a result of 1, then we know that that's a happy number by definition. Now, if at any point we get to a number that we've already seen, then that means that we're going to end in an endless loop. We're going to have a loop constantly going, right? If we have, for example, if we have a 60, if the 68th number, we keep on going, or like let's say x is the number, just an example, and then we keep on taking the sum of the square digits, keep on taking it, we get to a number that we have already seen, right? We're going to keep going in this cycle, right? We're going to keep on going in this loop. So that's never going to be a happy number. So that's how we detect that. And so if the result is in the tracker, that's how we keep track of the sum of the squared digits. If the result is in the tracker, then we're going to result in an endless loop. And so then we'll return false. It's not a happy number. And then if our result is ever 1, we're going to return true. And we're going to do this like around 10 times. So if in 10 iterations we don't return true or false, we're just going to return false. And again, this 10 is not programmatically it's decided. This was just as an experiment, and we saw that, hey, 10 was a valid number to pick. Just because like the digits didn't go that far deep. So there's 3 key points when we're doing this problem. One is adapting to the limitation of the problem. And this is specifically referring to the fact that we've done this iteration 10 times, or 10 was the number that we had chosen. And the reason that we picked 10 is because that was per the limitations of the problem. There wasn't any number where we constantly had to go to the sum of calculate the sum of the square of the digits more than 10 times to get to either a point where it repeated in a loop or to get to a point where it was 1. And so because of the version of the problem, we were able to take advantage of only doing it 10 times. Second is knowing when to stop. So the reason that how do we know when to stop? We knew when to stop because we were able to find a pattern of when it was not going to be a happy number. And when it was not going to be a happy number, it was through the entire loop, right? If we get to a point where the sum of the square digits, the result is the same as what we've already seen before, that's going to end in an endless loop. So that's knowing when to stop in this problem was a critical pattern recognition idea. 3 is having a helper function. This while loop would have been a lot more difficult to create if we had everything in the while loop. But because we've created a helper function to get the sum of the squared digits, in terms of how we're thinking about the problem, it makes it a lot easier. So having a helper function, breaking a larger problem into smaller subproblems that you can individually solve, and making those separate functions, and using those to your advantage to help simplify the problem, to help showcase your steps, is going to make your reasoning a lot more clear and your approach get a lot more have make your approach more clear and readable to other people. So with that, that was the end of this video. Hope you enjoyed, and I'll see you in the next one. Thanks. Bye.